Hello everyone. Today we will have a walkthrough of Vortex. This is an interesting paper from Google on big data, especially related to stream processing. Okay, so if we look at the paper, it has multiple sections. We will go through one by one. But just to understand the paper better, we have to first understand what this paper is related to. So this paper is related to BigQuery and the new features related to streaming ingestion. Okay. So before we have a walkthrough of the paper, let's dive into a bit of BigQuery, what is the use case of this paper, and then we will have a walk through of the paper, various sections, and we will look at all the architectures and all the results related to it. Okay. So let's see what this paper is related to. This is for Vortex, which is the system, the storage stream oriented storage engine behind the scene BigQuery. So as of now, we have seen multiple BigQuery components, right? Colossus, Dremel, Jupyter, then Capacitor, all of that. And mostly BigQuery is a cloud data warehouse. So, but nowadays we are looking at more and more of streaming use cases. Okay, so the general use cases for streaming are log analytics. Okay, so the systems are generating logs, or maybe some different applications are generating data and logs, and we want to perform analytics on top of it. And we have certain systems which are specialized in those areas. Example is elastic search. Okay, then we have certain real-time events happening in applications, and we need that data for analytics, and again perform analytics and then send it back to the other systems, or maybe the application, back to the application for real-time fraud detection, or those kind of scenarios. Okay, and the typical use case for streaming data ingestion into data warehouse systems is change data capture. Okay, so most of the time the data is coming in from databases in the form of change data. Those changes happening in the databases in insert, updates, and deletes, they need to be captured in real time, and then they are ingested onto data warehouse for performing all kind of data warehousing, business intelligence, and as well as real time reporting. Okay, so for change data capture, the open source frameworks enterprises use are Debezium, Kafka, like, and Spark or Flink together. Okay, so if the organization needs the data change data to be captured real time but ingested in batches, then the framework would look like CDC based on Debezium. And if they are using some of the proprietary tools as well in place of as a CDC system, which captures those database changes and push them onto Kafka or similar messaging systems. And then from there on, if the organization need the data to be processed in batch, then they generally use Spark. If the data needs to be materialized or take effect into the table in BigQuery, they would use Flink. Okay, and if it is a real-time event data ingestion, then like most of the times it is Kafka. And in then once the data is in Kafka or in GCP systems, it is PubSub. Then the next step is to process the data or perform analytics using Flink, or maybe data flow, or the data is once loaded onto BigQuery, we can perform ELT, all of those kind of scenarios. So for data warehouse point of view, CDC is the main use case where we generally use streaming. And for enterprises building data products which are catering to real-time systems, they are mostly real-time applications fraud detection or log analytics, or different kind of use cases, right? Where let's say ride hailing apps want to detect frauds and all financial systems, all of that. Okay, but when we ingest the stream data to make use of that data for further processing along with the existing data, there are certain challenges we face. Okay, like we capture the data from the source systems and use that for further processing. In between, there are multiple systems involved. Okay, if it is elastic, then there also it uses log stars and bringing them onto elastic, and those are again specialized systems we have to build to handle these. Okay, so the challenges mostly is latency and data freshness. Like if it is elastics, the data may take effect very fast, but in case of other two, if the data needs to be available in data warehouse to perform analytics, and then that data after processing data needs to be used in further downstream, then there is a lot of latency added during each of the hops. Like Kafka pops up, or then further processing using Flink or Spark, all that add latency to it, along with data quality issues as well. Okay, so data duplication issues and all that merging of various database changes, insert updates, all of that will come up. Okay, then the another challenge is with the data copy. Okay, with each hop the data is copied multiple times. Okay, and managing and data governance on each of them is a challenge. Okay, so these are the challenges we are facing. So for BigQuery as of now, it is mostly like batch processing for data warehouses, but more and more as we see data like organizations are trying to leverage the stream data in real time. Okay, so that there is a need for the data to be available on the data warehouse very fast and without specialized systems uh, to avoid all the data copy, data governance, and data quality issues. Okay, to handle or to cater to those kind of scenarios, BigQuery has added or introduced another storage engine called Vortex, which is streaming oriented. Like the initial use case it is used to solve is the streaming data ingestion, but it also can cater to batch data ingestion as well. Okay, so let's see like what are the features. Again, as we say, like it is the primary focus is on the streaming data ingestion, so that like as and when the data comes in with minimal latency, the data should be available for querying in the downstream. Okay, again, because the focus is on ingestion, it has to be write optimized. Like BigQuery is mostly performing analytical queries on huge amount of data, basically read optimized. Like on huge data you can query faster, but the Vortex feature is write optimized. Like as and when the data comes in, it has to be written in, and that data needs to take effect or committed, so that when the user executes query on the table, the new data, the streaming ingested data, shows up very quickly. Okay, again, unified API for batch and streaming, and asset, right? Like the streaming data comes in, it has to be compliant to the transactions. Okay, so due to these all features, like Vertex has created its own area in the whole architecture of BigQuery. Okay, so along with these Vortex, which is more related to BigQuery, what are other systems that are present in the market to solve these kind of streaming data handling. One is Kafka and Pravega, which are mostly like messaging systems where which act as a central storage systems, or you can say storage tunnel, where you put all your data, publish your data, and downstream or other systems read the data from it. Okay. Then Elastic Stack, which is mostly like log analytics, real-time logging. But again, those are specialized systems to perform, and mostly like semi-structured logs to do NLP and kind of searching on them. Okay. And let's say we want to build streaming through existing systems or the systems we use for batch processing. One of the scenario is Spark streaming, okay, which is micro batching. Like it handles, like stores the data for a certain period, and then like as a micro batch it processes, even though the micro batch is of very low time frame, which like gives an impression of streaming, but it is again micro batching. It is not true streaming scenario. Another like systems or a database we have seen is a Rockset, which is a true again streaming system for performing analytics. Okay. Nowadays with AI, the ingestion and analytics of data in real time is very important. So Rockset, you must have heard like related to OpenAI, which they have acquired in their more focus on the real-time data with respect to AI. Okay. Now let's little deep dive into BigQuery's architecture. Like you can find more videos or tutorials on BigQuery, but I will just go through just a brief of it. So when a user fires a query, that comes to Dremel, which is the query engine, which again a series or a collection, which is a distributed query engine which runs on slots. Okay, slots are nothing but compute, like some amount of compute and networking along with it to perform the computation. Okay. And the Dremel engine behind the scene generates the plan and runs the query in distributed mode, like a tree structure of the plan. And then those leaf nodes communicate to the Colossus, where the data is present in capacitor format, and perform the calculation. And once those like individual tasks are performed at the leaf node, then they further up in the tree, the mixers are there which perform the aggregation and return the results to the user. Okay. And all of these are orchestrated using Borg. Okay, which is again Google's you can think Borg as a Kubernetes engine, like provisioning all of the servers and maintaining them or orchestrating them. Okay. And all of the data shuffling between these compute or the slots happen through Jupyter network, which is like a high petabyte network to transfer the data between slots or the compute when they perform different operations. Okay. So how the query execution happens, like whenever a query is fired, the query coordinator parses it and creates the logical plan. Okay. Once the logical plan is ready, then it applies certain transformation like push down optimization and filters on it to create an optimized, little more refined plan. Then using the metadata it has, again metadata handling is a separate piece within it, but the query coordinator fetches all that metadata. Using that, it creates the distributed execution plan, and that is copied over to the slots or the compute. And the DAG of like execution plan is like executed on the compute on the workers or the slots. Okay, and again the leaf node perform the more granular work, which involves the reading data from Colossus, and then initial filter and those kind of parallel work, and then once the data is ready, the higher nodes or the mixers perform the aggregation on them. Okay, and at the end the final aggregation and all of that, if you see the BigQuery UI, you will see all of these as stages happening within it. Okay, now we looked at an overview of the BigQuery architectures, right? So all these happening in the read kind of. Okay, when we want to write to it, okay, so there is an API through which we directly write to Colossus. Okay, bulk interface, like bulk write interface is there, which writes to Colossus. Here it talks about reading, but writing is, there is a bulk API, but there is another streaming ingestion API is also there. Like generally the you can say storage write API, which also can perform the streaming ingestion. Okay, so this is how it looks like for the Vortex. So let's say the application client or a user trying to write perform the real-time ingestion into BigQuery, they would use the write API to ingest the data in real time. When the data and that API is part of Vortex client library, which also again has both write and read APIs. We will look at read API in a bit. Okay. So the whole system, if you see here, the Vortex client library, the APIs, the stream metadata server, stream server, and the write optimized storage and storage optimization service. These are your part of the Vortex. The other pieces, Dremel and read optimized storage, are existing, like the batch processing, right? Already they are there. So this is an additional piece of infrastructure which specially used for your streaming ingestion. Okay, again if we see the read happening, like once the data is written to the write optimized storage through this, now let's say at the same time a user is firing a query onto Dremel, again which goes through Dremel. It uses the data both from write optimized storage and read optimized storage as an union. Like how this happens, we will look in the paper, but you can think of it as an union of the data present in write optimized and read optimized. When the data is committed in the write optimized storage, there is a service for storage optimization which reads the data, the committed data from write optimized storage and write to read optimized storage, which is again Colossus. We will see the implementation of these in the paper, but again behind the scene, again the write optimized storage again uses Colossus only. Okay, but there is a layer in between which handles the data which is very performant for write. Okay, certain like data structures or components in between which handles the stream data ingestion. Let's say a client or an application writing to BigQuery in a streaming mode, streaming data ingestion, it would create one or more streams. Okay, which is again nothing but an entity or like maybe a specialized data structure within it, which is like a you can think of it as an queue or a list kind of structure which starts from 0, and from there on it like 1 2 3 4 it goes on, and it has a end point. Okay, and the data has to be appended at that point. Okay, we will see that offset mentioned in the paper. And each of the streams, like clients writing to the stream will write at that offset and update, like kind of the offset will get updated uh, based on the number of rows written to it. Okay, and the stream is again formed using one or more streamlets. Okay, because all these happening on compute, right? Some form of compute, so multiple compute are like spread across in a distributed manner. So maybe one or more in the system there can be more than one streamlets, but which has the same data, but only one is writable. Because to be in a distributed scenario, or a system handling failures and making, like keeping copies of data is very common, but only one of them is writable. Okay, and each of the streamlets again consist of fragments, which are nothing but like continuous blocks of rows, which are stored in log file, and that log file is handled or stored on Colossus. And each of the fragments or which stores or the fragments of log files of 2 MB in size. Okay, and this offset we will look at in the paper itself, so that it will be easily understood. Now type of streams, just to give you a brief. Unbuffered means as and when some data is written to unbuffered stream, it will be committed like instantly. It will show up to the user, or maybe very fast. Okay, as and when it is written to the stream, that will show up if we query on the Dremel side. Okay, buffered means it will wait for commits. Like how it happens we will see in the paper, but there are these are three type. Again, pending means one whole stream will stay alive for a long period of time when the data is coming in, and at the end it will commit, and the data gets materialized. Okay, so we will look in very detail in the paper itself, but just to give you a little bit overview of it. Okay, so you can think of stream as this kind of structure where it starts from 0 1 2 3, and it, let's say this is 2, so the next time the client tries to write, it should write at this point. But let's say, because this is a distributed system and multiple one, not just multiple, a client can write in parallel to the same stream, right? So during that time it can, like let's say it is 2 now, but new data comes in, 2 records more added to it, it will become 4. Okay, so there is another thread, or in parallel the client is trying to write. The client can write at 6. Okay, so that one client one parallelly can run to 2 and 4 simultaneously, and no need to wait again. If they try to write simultaneously to 2, it will fail. Okay, so that is how these based on number of rows, these offsets are calculated, so that multiple in parallel clients can write to these streams. Okay, so again these are mentioned in the paper, like how the stream gets created, records get appended to it, and the flushing, committing, and finalizing. Again, if you see this flushing, committing are kind of how it relates to your types of streams, as well as how the data gets materialized or committed and end of the stream. Okay, again as we like talked, the mostly the Vortex uses the write optimized storage. Main reads are present on Colossus for the users to query, but when the data is still in write optimized storage. It is the Vortex client library which talk to these two storage points and make sure all the data from both these storage systems gets unioned and source up in the query result. Okay, so let's go to the paper itself. So the first part is the abstract. Again, it talks about why the use case or the need for Vortex. Okay, data analytics over continuous streams. Okay, let's see. Again, it talks about how data warehouses are mostly like focused on batch processing to handle streaming in the data warehouse. This Vortex storage engine is built. Okay. Okay. So again, it talks about data warehouses and kind of operations happen in BigQuery, like partitioning, clustering. We talked about the streaming challenges. Again, like freshness, latency, when we try to use batch systems for stream processing, there is a lag, as well as, let's say, the streaming system is trying to write, and there is a huge amount of data coming in. Okay, it has to be buffered. Okay, and that is again a storage challenge at the source side, and if we try to handle through sampling, there is a data loss and data quality issues. But we need all of the data, right? We cannot like always use sampling. Okay, then again, data copied between data source till data warehouse, multiple places it is written while it hops through the messaging system, then the material system, and then warehouse. So all that like adds to the latency and efficiency. Okay, this is like the features of Vortex. It talks about ACID compliance, unified API, and scalable, like because it handles all of the handling of streaming data ingestion, materialization, and distributed management of data. All of that it handles all in itself. It is very scalable. Okay, and then performant again, all performant in the sense, like if you are performing a large transaction, it still works very scalable manner, as well as if you are performing very granular level transaction, single row updates, deletes, insert, all that also works very fine. Okay, and then the related work, we talked about Kafka, right? And then we talked about micro batching, and then Rockset. Okay, so these are the some of the systems, and also Elastic Stack for the logs analytics. These we already talked about how they are related, solving similar problems, but because the focus is more here on BigQuery natively supporting data ingestion for the streaming data in the data warehouse. This is how different challenge. Okay, again, background of BigQuery. We know of the storage system Colossus, then Dremel, we have the Jupyter network, then we have, and like how the downstream systems connect to BigQuery and use it for querying, and the data bulk loading and streaming ingestion. The more focus is on the streaming ingestion through this paper. Okay, so again, this talks about how the query gets, the logical query plan gets created, and how the like at the end how it works, interacts with the storage engine, like starting from the query till how the logical plan, then use of metadata to create distributed plans and DAG stages. and finally executing the query, and that those leaf node interacting with the storage system in parallel to read the data and perform the work. Okay. Now the interface for Vortex starts with the storage engine, where like if we perform the streaming ingestion, this is where it all starts. Okay. Again, like the specifications or the content, if you see, it is all how generally BigQuery handles data. Like if you have worked with BigQuery already, it has the concept called dataset. Okay. Which again contains all your tables and materialized views. Okay. And you use your APIs or SQL to perform work. Okay. So if you see here, again, write API is mostly for your real-time data ingestion and analytics. That is where your all Vertex behind the scene works. Okay. Again, it talks about the storage for file system behind the scene for BigQuery's courses. Again, asset compliance. You can look through all of it. Like this is general BigQuery related. The file format that is used within BigQuery is the capacitor. If you are using Big Lake, then maybe it is different, but the native storage uses the capacitor. Okay. Again, big metadata. If you see this, again, there is a paper for this as well. Again, when you handle data at large, the big data, and in a distributed manner, the metadata itself becomes very huge. Okay. This is one of the challenges even other big data systems face when they kind of handle, like you must know the handling of metadata in Spark, and the more and more small files get created, the metadata also gets used, and all of that, right? Similarly, the metadata related to all of the housekeeping in between, how to transactions and files moving around, getting committed and combined, all of that. Like, and the metadata has to be scalable so that the query will be faster as well. If you see, metadata has an impact on the query performance as well. Okay. So again, now from here on, it talks about the Vortex, which is the key component within storage engine itself to handle the streaming data ingestion. Okay. So let's see. Stream, this is the basic entity on the data structure which is used for handling your streaming data through Vortex. Okay. Each row in a Vortex stream is identified by the streams identifier and its row offsets in the stream, right? We looked at this one. Okay. So if you see, if we see this one, it starts from, it will have an ID. This stream will have an ID which is related, like the client would know this is the ID for that client, and these are your offset 0, 1, 2, 3, and the data gets appended from this end. Okay. So that is what it tries to say. Okay. Readers can concurrently read a stream at different rows offsets. Like there is in relational databases also, the order of the rows like doesn't matter, right? So the reading is hardly affected, but the write, it all depends on the client, and it has to be written based on row offset. Okay. Again, it says a table is an unordered collection within a stream. When a client process wants to write, uh, it would create one or more streams. Again, parallel writing more than one if it is like simple, or just one uh, way, like one only, not parallel, then only one stream. Okay, tens of thousands can create concurrent, thousand clients can concurrently write to a table, each of them typically using their own dedicated system. So one client can have multiple streams, but they are exclusive to that client. Okay, like one client cannot write to another client stream. Okay, and multiple streams can be there if they are writing in parallel. Okay, now let's see the APIs. Stream creation. First API is for the stream creation. If you see, it talks about three type of stream creation. One is unbuffered. Okay, when it creates the unbuffered stream, there is one append stream. Like the append stream is for all of the three. Just let's see what it does for the unbuffered. Okay, when an append stream request returns with success, means let's say the client request through append stream interface. Okay, it indicates that input, and it succeeds with then it indicates that the input rows provided in the request have been durably committed to Vortex. Okay, they are not in memory, they are committed to Vortex. Okay, now what that mean we will see when we query it. Okay, but as of now it means it is committed to Vortex. Okay, it is durable now. Okay, it can't like something happens to the system, the data won't get lost. Okay, any subsequent reads from of this table guaranteed to see these rows. Okay, a user tries to read, the rows will show up. Okay, so as and when the rows come up, they gets committed and they show up in the query. Okay, unbuffered, straightforward, as and when it comes. Okay, any now second is in a buffered stream. Okay, when that request gets successful acknowledgement, okay, that means input rows have been written to Vortex, but they are not committed. Like it is happening in memory. Okay, they are not the user. If the user tries to query the table, the user won't show these rows. Okay, these rows are not visible to subsequent reads until they are flushed. So there has to be one flush operation, only then it will get committed, or like the user can see that data. Okay, like how the flushing happens we will see in in the subsequent subsections. Here we are only talking about the creation. Flushing we will see in a bit. In a pending stream, rows are not visible until the stream is committed. Okay, again committing is another operation. We see flush, another is committed. These two operations are related to the buffered and pending, so that like in flight data handling until it shows up, like it gets materialized or committed, then only it will show up, right? So these two operations we will see later. Okay, again this is a pseudo code, how it does. Appending rows, again we talked, right? Each stream has one identifier and row offset. Let's say if it is created for the first time, it will start from 0. Okay, so it would have the ID. So when the client writing to the stream sends the data, it will use the offset to write to it. Okay, again the data is in binary format, and it when written to the stream. Okay, other data types also, like data formats are supported, but here let's say we assume binary, but different are supported as well. Okay, here little bit of layering, like where it happens. So at the end, if you see, all of it is on Colossus only there is a layer in between your Colossus and the storage engine, through which there are certain processes and certain layer of data handling, data structures, which ensure that it is right optimized. Okay, now the row offset is optional. If you see here, when the append stream is used, this rows offset is given, but it is optional. Okay, let's see what is the effect of it. Okay, allows the client to specify the offset in the stream at which it expects the rows to be appended. Like it will tell, as per this system, let's say it gives 2, that means you have to append it 2, and here on. Okay, like number of records. Okay, so basically it has one single append point. After that, all the rows it has, it will write to it, and it is most of the times end of the stream, always at the current end of the stream. Okay, we call the number of rows written to a stream is the current length. Okay, number of rows already in the stream, already written, is the current length, and based on that your offset is there. Okay, using an append offset that is different from the current length of stream will result in an error. Okay, again, total number of records in rows in the stream, from that will be used as an offset. Okay, if you try to use anything else, it will fail. Okay, essentially, if multiple writes, okay, whether it is different clients or same client, okay, tries to use same offset, only one will succeed, others will. So this is related to your like exact ones semantics. Okay, how that is being used. Yeah, if you see, this talks about exactly one semantics. Okay, so when the rows come in, they will have the offsets, and the same record, if it comes in within the stream, in the append stream, okay, then like 2 records will have same offset and it will fail. So to make sure that only one time it gets written, this row offset is used. If you don't use it, it will become at least once. That means you will have multiple records in your data. Okay, again, pipelining, it talks about how parallelly it can write. Like if the current length, pipelining means to the same stream, like if we have multiple offsets already determined through the data, then multiple clients can write to different offsets in parallel, but they cannot be like overlapping. Okay, so it says one stream has a row, like 4 rows are already there. Now first client tries to write to 4. Okay, then subsequent append stream call that wants to append at the next 5 rows doesn't need to wait. Okay, so let's say that first append has 10 rows, so it can write from 4 to 14. It knows that there are 14, it will become 14, and the next other parallel client can write from 15 onwards. Okay, or the offset at 14 it can write. So parallelly they can write it, one at 4 and one at 14. Okay, that is how it talks about like parallelly multiple can be written into the stream. Okay, flushing of a stream, recall that data returned to buffer stream not committed until it is flushed. Flushing, again, it is an API. That means flushing this function, or it is called. Then if it success, return success, it indicates all the rows in the stream up to and including the row have been committed. Okay, so basically in between it can run flushing so that some amount of data can be committed. Okay, because it is buffered, maybe more and more data coming in, but some of the data from that stream to be committed. Okay, so it uses one flush stream and the data gets committed. Okay, row offset, based on that it gets committed. Okay. The next is committing. Committing means data returned to pending streams are not visible until stream is marked committed. Okay, a command pertain with batch processing multiple workers independently, right, to the in order to achieve atomicity pending stream. Okay, so this is actually like writing to the durable storage. Okay, again, handling the atomicity. This commit is happening. Okay, anything else? In order to achieve atomicity, these parallel distributor writes, each worker creates pending stream. It writes all the data to it and reports its completion to the coordinator node. When the coordinator receives success from all the workers, it issues a batch commit request to Vortex to commit all the streams atomically. Okay, atomically means all at once. Okay, so basically fragmented, they try to, like, at each worker level they try to write. Okay, when they send that request and of committing at each worker level and they get a success, then a batch commit request is given so that all of the data streams data gets committed. Okay, then it gets like the data shows up for the user or the reader who reads the data. Okay, finalizing a stream. After a stream is created, a client can write to the stream forever. Okay, when the client has finished writing it, it can finalize the stream to prevent. So basically this is end of the streaming. Okay, so committing is writing, like end of writing. Maybe if it is writing in batches through flushing, then it can be end of the data cycle, but this is end of streams life cycle. Okay, mutations, again, mutations means insert, update, different changes to the data. Again, it uses the interface for append stream. If you know of how different CDC are handled, you would see this kind of meta columns in there as well. Here it uses the virtual column or meta column kind of change type to handle, like if it is an insert, upsert, or delete. We will see towards the end how these are handled. Like upsert, you would know, like it handles generally in is like insert and delete, right? If for updates it is delete and insert new records. If it is insert, regular append. Delete means it will mark those records delete and later it will do the garbage collection. Okay, so yeah, we talked about streamlets, like multiple streams behind the scene use streamlets, and they are spread across multiple clusters. Okay, within BigQuery's compute, multiple regions, clusters, so that, like, in a distributed manner they can have copies of data. Again, order list of one or more streamlets, but the more important thing is only one is writable. Okay, like even if there are multiple streamlets, only one can be written into, not all of them. Okay, fragments like contiguous blocks of rows which are stored on log file, and again log files are stored on Colossus. The data is in binary format. Okay, write optimized storage, read optimized storage, capacitor, and for native, and if it is big lake, it uses Parquet for read optimized storage, which is on Colossus. For write optimized, again it uses all of these log file based fragments and everything. Okay, there are two pieces to this architecture. Again, control plane, which is like coordinating all the processes and everything, and the other is data plane. Okay, so the control plane is handled through stream metadata server. Like whenever the stream ingestion comes in through write API, it comes to stream metadata server first. Again, there is a cluster of these services which handles these. Like you can go through it, but you can think of it as multiple instances of the same service to handle different write to different places. Okay, distributed computing, simple. Okay, the request comes in from write, and they come into these more or a large number of SMS, Vortex SMS, they call it, stream metadata server, through which it coordinates all of that. Okay, and but actual writing of log fragments are situated at this stream server, and they are stored on Colossus. Again, if these are Colossus, these are also Colossus. Only this piece of storage like SMS and stream metadata server and the stream server are the two things that handle the writing into an intermediate write optimized storage, so that the writing is faster. If you see in this architecture, again, when the read query is happening, this Vortex client library is taking data from this write optimized storage and read optimized Colossus, and then sends the data, and the data has to be committed here. Okay, then only it will show up, otherwise it is not here. It is here only already, not shown to the user. Okay, data plane again talks about how the streamlets fragments are handled. You can go through it, like more detail are there, but you can think of it is where this handles all of the streamlet fragments and your log files. Log files are on Colossus here, but fragments and everything, how to stream is written to the interface is handled here, the writing process. Okay, but like once the coordination is given to the stream server, like once the write request comes in, initially it assigns the writing or the fragments and streamlets here. Now the client can directly talk to stream server. There is no need of this component. If you see, all the data writing happens from the client to the stream server. There is no role for SMS again, until unless there is a failure and some data consolidation need to happen. Okay, so you can think of first coordination, giving the work of writing or managing the stream here, the data is here, and once that is done, the writing communication is happening between the client and stream server. Okay, client library, again API is handling how it happens. Okay, there are multiple features to it, schema evaluation, unary, binary, bidirectional RPC. There is some significance to it, like how unary and bidirectional, but let's say multiple clients are trying to write, there will be a lot of writing patterns are there, uh, but to handle efficiently these connections and better utilized, only few of them are like used for bidirectional communication, and mostly are unary only. Okay, they are killed if they are not needed. Okay, only bidirectional for certain scenarios. Okay. Yeah, you can read through more, but on an overall, this is like lifetime of a data, all of the heartbeat, and to make sure the stream server is there and doing the work. All the SMS, Vortex SMS is coordinating to make sure it is there. Okay. Fragment file system, like file map for disaster recovery. Again, it talks about 2 MB size. If it is over it, then it will create another fragment. Okay, so only one will be active, others are like only there. Okay, like when the flushing happens or committed, it gets committed, those are cleaned up in a, and written to the read optimized. Okay. uh, there is a little hardly, like these are simple things, not simple, how it handles the disaster and all is there. Okay, now coming to the storage optimization, right? We talked about this. If we see this write optimize to read optimize, there is one service running, right, which takes the data and puts here. Okay, for longer durable storage for reading, which are optimized for reading, not writing. Okay, if you see, it again uses this timestamp. Like here we saw only like a stream in this format, right? If you see, these are your streamlet. Okay, and then with in them there is fragments. If you see here, fragment A, B, C, but A, B are like, let's say they are more near to 2 MB, so they are not active. Only this is not up to 2 MB, so it is getting written into. Similarly for here, this is the active one, this is already written 2 MB. Okay, now it will gather all of these data and create to the partitioning. Again, read optimize means in the Colossus the tables are partitioned and clustered. So this is one scenario of partitioning. So it gathers all of the data based on, let's say it is based partition on dates, it will gather data from different fragments, related data, and puts into one partition. Similarly for the other partition. For clustering, again, if this data is there, okay, it automatically performs the clustering as well. Like if you see, for each of the clusters, this min key, max key changes based on the data coming in from here. Okay, so basically it is doing the automatic reclustering if the table has the clustering on it. Okay. Metadata management, it uses the big metadata. Maybe someday we will again look at the big metadata part, but yeah, the scalable big metadata, mostly it uses spanner behind the scene to handle all of the data. Yeah, repartition elimination. Yeah, here if you see how it handles the mutations, update, delete, and merge. Okay, so delete is a kind of marking it delete in the fragment. Okay, update is implemented using delete and insertion. Okay. Yeah, exactly one processing. Again, we talked about the offsets and everything, right? So exactly once means the offset is used to make sure that uh, it only gets written only once. Okay, it again talks about the data flow side of it. Okay, Okay, end to end of both ingress and egress, means writing and reading together with data flow. Okay, but that's fine, how that is achieved. And this result page shows up like how queries latency of append, okay, based on the volume size of the data and the rate at which this is latency, and what is the volume of data that is being appended. Okay, so mostly if it is very less data, then it is in millisecond, very less, maybe 1-2 millisecond. But if it is more than 1 gig per second, then it goes up to some 10-20 millisecond. Okay, yeah, so this is all of it. You can like overall this is the idea of the architecture. So you already have maybe we can see the structure here in the architecture. Okay, so this part is already there just for making sure the string input is performance scalable and without any external handling this merge of CDC data or ingestion. uh, New changes coming in gets affected in the data warehouse in a scalable manner. This is the structure it uses. Okay, so these client library, Vortex storage, this stream management metadata server, and this piece, okay, of it is the piece that performs this in between write optimization, as well as materializing into Colossus for reading. Okay, in other systems also we see that let's say someone is building their own custom system for these. How they do is they read it into Kafka or PubSub, then maybe intermediate they write into Parquet, or maybe if it is nowadays we have different file formats which do the transaction handling, maybe Iceberg or delta tables. These are kind of systems also support uh, real-time data asset properties, maybe transaction, but real-time how they are performant, not performant like these, but somewhat it is. But because of the data structure it uses, these are performant and can handle petabyte scale streaming ingestion. Okay, so overall these are the nuances and various components and how it works. Okay, if you go through all of it, you would maybe this video will help you as a overview to understand various components. Maybe you can read through more detail. There are various technical things as well into it. You can tie them together. Okay, yeah, again one of the more interesting pieces is these references which it uses. You can go through them, like how Colossus works, and like again it has how query works in BigQuery, all of that, the file law, LSTM tree, yeah, so all of it is there. Okay, so hopefully this overview will help you to read this paper on your own, to read the jargons as well, understand how it works. Okay, yeah, hope you like it. Okay, if you like it, then you can share it with others as well. Thank you, bye.